I don't prepare too much, it's a post about what I learned from algebraic geometry, and it's still under review. I think there's some mistakes in this post, and I think it's good material to begin today's talk. So it's just to recall 2 weeks 2 weeks ago, I just used whiteboard to describe some properties of affine space and projective space, but it's not clear. So I just want to quick review the talk 2 weeks ago. So we have two space, affine space and projective space. They have different symbol. For affine space is symbolized by a big A with n, and n is a positive integer. And the projective space is also symbolized by a big letter, a big P, where n is a positive integer. But the difference between these two space is the element in affine space is you can think it's a point, and the element in projective space you can think of as a direction. So if you so that is why the element in the point in affine space is have n coordinate, and the point in projective space it has n+1 point. The n represents the dimension of the space. So that is it. The projective space have some properties because every element in projective space has its direction. So the property 1 says if we have any non-zero lambda, and we can multiply the lambda to each coordinate, and we get a new point, but the same element. And so that is the basic property of the projective space. Another thing you need to mention is there's no all 0 point. That means all coordinate is 0. That point it doesn't exist because it can be counted and as any element. And the property 2 is it's the relationship between same dimension affine space and projective space. There is a relationship here as a show. This is very important because we can have some conversion between we can convert a curve in affine space to a projective space and back to and a curve, a curve in a projective space to map back to the affine space. So it's a very important relationship. But how we can clear the relationship? We have two cases. The first case is if xn+1 is non-zero, we can let lambda is equal to 1 over x n plus 1, and we can get another equivalent point to show that this one has a relationship with a n, and if xn plus 1 is 0, and we can we already clear a coordinate, a variable, and we can, if we have this form, we can multiply other lambda or other non-zero lambda to other point. So it's exactly another projective space with n dimension. So these two cases to show the relationship between projective space and the affine space, there are some concept of the relationship. The infinity of P1 is called infinity point, and the infinity of P2 is called infinity line. So the infinity point is very useful in the in these concepts. Yeah. And property 3, we have some polynomial defined in project space. The polynomials should be homogeneous, like each term has the same degree, like x1 plus x1 multi x2 plus x3 square. As you know, x1 is with degree 1, x2 is with degree 1, and the term is degree 2. So so each term should have same degree. Okay. Yeah, so by applying the property 2, we have any homogeneous polynomial. We can add a non-zero lambda, and it's equal to lambda to n plus 1, and multiply f. Why this property, this property is useful? It's because it can be well defined in rational map. That means if we have two curves in the same space and we want to map a curve to another curve, and it will be very useful, because if we multiply a lambda to the original curve, we multiply lambda to every coordinate of original curve, and it will show very useful. It's a very useful tool for that construction, and we have an example of this two space, and people love example, and for a circle curve we have just show we have two forms of representation. The first form is x squared plus 2y squared is equal to 1. It's obviously defined in affine space, because we don't have a non-homogeneous polynomial in project space. While another form of circle curve is x squared plus y squared is equal to z squared. It's defined in project space. We can show we have the same number of points between these two forms over Fp. Okay. Yeah, we just apply the property 2 we mentioned before. We can when z is non-zero. Okay, we can highlight this. When z is non-zero, we can change coordinate to this form, and by multiply 1 over z. when z is non-zero, we can get x squared plus y squared is equal to 0, which means x and y should be 0. Because we calculate this over fp, so this case we can find not non we cannot find any point in the affinity line at the affinity line. That show we have the same points on these two forms curve on this two between the two forms of circle curve. But if we change our base field, we can find something different. If we taking fi as example, that means the base field is f, and we can construct an extension field by drawing I, which I is root of -1, and we can find the equation x squared plus y squared is equal to 0 have two solutions. The two solutions is defined by in the paper defined by infinity and infinity bar, and these 2 points can be calculated very simple. And if you find some other solutions like 2 minus 2i 0, the point it can be it's equivalent with the infinity bar. So far, any question? It's still under review. Okay. Can you still share the link? Even though it's under review. Okay. And we can continue. And how much? 4 minutes. Okay. So we can quickly review other part of the article. The second part is coordinator is morphism, and we should define many concepts to define a morphism. And the first the morphism is actually it's used to define the map between curve and the curve. The morphism is well rational map to define this this map, but we can directly show some cases and skip these concepts, and we can show this one. If we have a map like this, we can map a circle curve to P1 by this map phi, and it should be a very useful map, because every point in the circle curve is mapped to a meaningful point in P1. So okay. So let's jump this directly, and finally we can find another meaningful map called P. Is basically mapped P1 at the point in P1 to the circle curve, and we combine these two morphism, and we get it's identical, and that means the curve is isomorphism. That's why the circle Stark paper that is the circle Stark paper not mentioned. And another word called the stereographic projection. It's actually the phi and psi combination. It's just another name. And for the third part of the post, I talk about the order function. It's about how to define a degree of zeros. So every point have we can define each point in the curve have some vanish. Just means if we construct a point to we can first we have some ideal of all polynomial for a point. That means the ideal is defined by this equation, and the ideal contain any polynomial that vanish at p. Once we get the concept, we can define the degree of the order. Like suppose we have some degree ideal, and the order of a function in the ideal is actually the exponential number of the generator. But we can skip this part, but we can find some useful properties of order function. If we have two polynomial and f and g, we multiply them, and the final order function of them is just the sum of each order function of the polynomial, and other properties is simple, because if you think the order of a function, a function vanishing at some point, and the order exactly is the exponential of the generator. So that's applied this thought, and we have some examples. The first is we can use the properties shown here, and we check by considering this this equation, and it can be read as x minus iy multiply x plus iy equal to 0 square, and x minus iy doesn't vanish at infinity. So the order of infinity, the order of the x minus iy at infinity is 0, and that means we change the equation, right? We can check the properties again, and we know the order in x minus iy is 0, and we can find the order of here. The order of x plus iy is to double the order infinity at double order function of z at infinity. So that means x plus iy should be at least 2. So that's some calculation to apply these properties, and we will find some good thing, and we'll just apply the trick to calculate the order function. We have many because we can define the order function at each point, so we can, and for each polynomial, and we just list all the function result here. This result will be used in the next part. So okay, so the final part is divisor. Divisor is just because we define integer, a relationship between integer and point. So the order function is just show the y, how to divide some we call the polynomial to because we have many polynomial, but we just want to subset of them. We can use, by using divisor, we can exclude some not good polynomial, and the divisor shows each point we have some integer associated with the point, and we can use the d to like this one. We can use the d to divide the function. If some function satisfies the relationship, and it can be included to the LD space, and this is a vector space. And finally, the Riemann-Roch theorem states that we have some relationship between the dimension of the LD and the divisor. You know, the LD is a vector space defined by a divisor, and the Riemann-Roch theorem says we have some relationship between the space of the dimension of the space LD and the divisor itself. So we can directly see the final result. The circle star case is this one. Okay, so the degree D, obviously, the circle star case is satisfy this case. So we can directly get the LD is equal to degree D minus G plus 1, and G is genus of the curve, so it should be 0, and the degree big D is a sum of, or like this one, of NP. So that means we can easily get the dimension of the vector space by this equation, and it turns out n plus 1. And finally, we have some example of the show why LD is this equation. It just appears in the circle star. Finally, we recommend some books to algebraic geometry. Thank you, everyone. Any question?